Hi, welcome to another lecture on business mathematics. We are going to continue our discussion we started last time about interest rate calculations. Last time I explained how compounding brings us to the example of application of exponential functions, and today we are going to take a look at applications of logarithmic functions. Exponential and logarithmic functions are inverses of each other, like multiplication and division. Whenever you see one of them, you are bound to see the other one as well. So let's go take a look at several examples where we can see how logarithmic functions come into play. So let's take our familiar example that we have a certain amount of money and we are depositing into certain account. One of the things we could wonder about is, well, how long would it be before our money doubles in that account? So that's referred to as doubling time. So suppose we have certain amount of money, as usual, let's take it to be $10,000. We are dealing with a bank that is willing to give us an interest of say 6%, which we have to write as decimals, 0.06. We are going to be compounding continuously. Remember, the formula for that was the accrued amount is the principal times the exponential of r times t. Question is, how long before our money doubles? So it's a very standard question in sciences as well as in finances. In finances, typically think about your doubling your money. In sciences, you think about half-life. How long would it take for a certain substance to disintegrate in radioactive interactions and such. Formulas very similar to each other. Here we are dealing with money and we are hoping our money actually to double. So what does it mean to double? It means the accrued amount is going to be twice the principal amount. So in this formula we have 2p is equal to p exponential of rt. We can divide both sides by p, which simplifies to 2 is equal to exponential of rt. We have the r. In this case, we have exponential of 0.6t. The question is, what is t in this case? Well, we take logarithm from both sides. So logarithm of 2 is equal to the logarithm of exponential of 0.06t. Well, this is logarithm of 2. We know from prior lecture, logarithm of exponential of x is just x. Logarithm and exponential are inverse functions of each other. Same way that you would say like cube root of x cube is x, because cube root and cubing are inverses of each other. In the same sense, logarithm and exponential are inverses of each other. So if they apply in sequence on same number, then the final number is same as your starting number. Same way here. So logarithm of 0.6t is just 0.06t. Now we have the rate. We want to figure out what the time is going to be. So t, we divide both sides. Logarithm of 2 divided by 0.06. So we go and crank up our calculator as usual. So my calculator shows 11.55 years. So at this rate, we are going to double our money in about 11.5 years. So that's a standard question in finance or investment. If you put certain money into a certain so-called instrument, after how long would it double? Notice that we didn't use the amount of principal in our calculation. When we divide it by p, it all canceled out. So in essence, we don't need to know how much money you're putting in. That could be eliminated from the discussion. It's irrelevant how much money you're putting in, because all that you care about is after what time it doubles. So you can answer similar question, how long would it be after the money triples or quadruples and so on. The only thing that is going to be different is that instead of logarithm of 2, you're going to have logarithm of 3 or 4 or whatever the multiple happens to be. So that was one example. Well, what if we weren't doing continuous compounding? What if it was some other kind of compounding? So suppose again, as we said, we don't need to know what exact principle it is we are dealing with. Suppose the interest rate is the same 6%, and we are compounding 4 times or quarterly. So same question, how long before money doubles? So remember, in that case, the accrued amount was the principal times interest rate, the nominal. So this is going to be nominal interest rate, because the effective interest rate is whatever happens during 1 year, and in business practices that's referred to as a yield. But at any rate, whatever R is divided by M, or let me write the general formula first. So M power of MT. That's for compounding M times a year. So if I want my money to double, means the accrued amount is going to be twice the original principal. This becomes P times 1 plus R over M to power of MT. We divide both sides by P, so as usual P cancels out, and for that reason I don't need to know what P is. Now we can go and take a logarithm of both sides. You can use any logarithm, natural log or any other log. It doesn't make a difference, so I just write logarithm. It would be same base. The important thing is that all the logarithms you use better be in the same base to avoid certain mistakes. So while on your calculator you have 2 logarithms, either natural log or logarithm base 10. So consistently use one of these two. Well, one of the rules of logarithm we had was that the logarithm of say b to power of x is x times logarithm of b. So in this case, this comes in front. Logarithm of 2 becomes mt logarithm of 1 plus r over m. Now I didn't put the numbers here just so that we practice using general symbols. That was 6%, that was 4, but it's all the same. So what is t? T is going to be the right hand side, which was logarithm of 2 divided by, well, the multiple of p is m logarithm of 1 plus r over m. So in our case, t is logarithm of 2 divided, m was 4, and logarithm of 1 plus 6% divided by 4 ways. So let me specialize to just one log. Let's say natural log. So I write natural log. You could use natural log or any other log, logarithm base 10, so long as it's the same one. So for natural log of that is 1.015. So let's go ahead and figure out what that thing is. So I typed this thing in my calculator and then I got almost 11.64 years. So how does this compare to what we had before? What did we have before? 11.55. If you do continuous compounding, that would be the fastest way of getting where you want to go. So that way you're going to finish faster. 11.55 as opposed to 11.64 now. So a tad bit faster by using continuous compounding. Now let's go ahead, take a look at another example. Okay, here's a problem from your textbook. How much money needed to invest now to obtain $5,000 in 10 years if the interest rate in a CD is a certificate of deposit? Like you put the money in, you cannot take it out, and the interest rate is a fixed number given at the very beginning. CD is 2.25% in this nominal interest rate, and we are compounding monthly. Round your answer to the nearest cent. So what formula is applicable here? We are doing monthly compounding. So in general, the amount is P times 1 plus R over M to the power of MT. In this case, we are given that R is 2.25%, which we have to translate to 0.0225, and we are doing monthly, so M is 12. To obtain 5,000, it means A is 5,000. That's going to be the accrued amount, total money that's available. How much money is needed means how much are you going to put in. That's the principal. So what you're trying to solve is 5,000 is equal to P, which we don't know, 1 plus the interest rate, which is 0.0225. M is 12. I forgot to mention here, of course, T, we are given 10 years. We are waiting 10 years, so M is 12 and T is 10. So this problem just becomes an example of exponentiation division. So P that we want to calculate, P is going to be 5,000. These parentheses, I go ahead and calculate the parentheses just to have it written in a bit of nicer way. So that is 1.001875, and then exponent that I have is 120. So I have this number raised to power of 120. That becomes 1.25. So 5,000 divided by 1.2520, etc. And then I take this number multiplied by 5,000, and I get $3,993.42, a little bit more. So you have to put almost $4,000 now, $3,993.42. You have to put that, wait 10 years, compound monthly 12 times a year, wait 10 years, and that amount is going to grow to 5,000. Notice that the interest rate is rather low here, 2.25%. In some cases that like when you're dealing with credit card companies, the interest rate will be 10 times bigger than that. It's not unusual for 22%, 30% interest rate, and that is going to have a substantial effect on you. So let me just as a matter of life advice, let me say, suppose you go to a dinner date and you spend, say, $50. You don't pay it on your credit card, and you got a kind of high rate credit cards, not very unusual. Suppose this is say 30%, so that is equal to 0.3, and then you keep ignoring this account for 10 years. And just to make it simple, suppose we do continuous compounding. So this is years, and suppose we do continuous, or you can do monthly, whatever you want. So how much are you going to owe? So remember, that was principal exponential of RT. So you paid $50 for that dinner. Exponential of the rate is 0.3, and you keep not paying this for a long time, for 10 years. So it becomes 50, assuming that you are not having any fines and you're making some minimum payments and so on. That becomes E3. So what is that? 3 exponential times 50, you're gonna owe a nice $1,004.28. So your $50 in 10 years grew to $1,004. So you're paying 20 times as much. The amounts increase due to high interest rate. Also, even if you have some reasonable interest rate, but if you wait a very long time, you are going to face some strange numbers. As a part of American history, you hear that the island of Manhattan was purchased for measly $24. The settlers bought it for that amount, presumably, is one story, from the Indians who were living there, and that's how much they paid, presumably. Over a long time, interest rate averages out to about 8%. Okay, so that's a discussion for another day, but that's about the average rate of return on the stock market over a very long period of time. Average is about 8%. Well, now we have a sticky situation. How about T? What is T? Well, that is the number of years since Manhattan was purchased. Now, we have to go find some historical document to see when did this thing actually happen. Let me see if I can figure it out. Okay, so the story goes that it was purchased by the Dutch immigrants from the Indians who were there, and they paid 60 Dutch guilders, whatever that is. So sometimes they refer to this as $24. It's a guess. The purchase happened in 1626, so that would be about 400 years ago, or 398 years ago, but just to make rounded up. So we have a long time to wait, 400 years. Well, the issue is that this looks very small, $24. We all wish we can buy an island of Manhattan for $24. But what if you have to wait 400 years to claim it? how much does $24 add up to if you put it into a bank account paying 8% continuous compounding for 400 years? Let's go ahead and calculate. It's all hypothetical, but just to see. Let's use the continuous compounding because it's simplest. Principal is $24. Exponential of R is 0.08, and the amount of time we waited, we approximated to be 400 years. So this becomes 24 times exponential of 4 times 8 is 32. So what is that amount? So let's go ahead again, find our calculator and punch it in. So I have, a humongous number. How am I going to write it down? So are you ready? 1.895 111,044 384 337. I don't even know how to read this thing. That's how many dollars that $24 is going to amount to, and I doubt that island of Manhattan is worth that much. So here is the moral of this story. If you invest in good time, your money, thanks to compounding, can reach extreme highs. Of course, you have to be careful about where you're investing and what you're doing with it. But if you do play your hands correct, you are going to be rewarded. That's a reason I tell you not to have any outstanding payments on credit card, because if this is working against you, in that case, instead of 8%, you have 30%, and as astronomical as this number is, that's even worse. And if you are working for retirement, you want to start early and set aside certain money and invest it wisely, and hopefully it will grow for you. So the moral of story is continuous compounding is, if it's working for you, is a major advantage. If working against you, is a major disaster, and you want to be carefully approaching the topic. Okay, until next lecture, good luck and God bless.